All right, so this is our last section for Chapter 15, Applications of Aqueous Equilibria. So we've talked a little bit about solubility at the end of the last lecture. So now we're looking at solubility and the common ion effect. We had kind of implied that this could work a little bit earlier, but now we're looking at more of the math of how this would be done. So if there were other ions present, if one of the ions here of the magnesium fluoride was present already in the system, then that would affect the dissolution of magnesium fluoride, because the presence of the other ions would shift equilibrium to the left and prevent dissolution. So they say here, because of this constant, if this increases, okay, this must decrease. If this increases, this must decrease, because KSP has to stay constant. Okay. So the solubility of magnesium fluoride decreases markedly upon the addition of fluoride ions. Okay, so that's interesting, but it's kind of just an application of Le Chatelier's principle and some of the other ideas we'd already seen. We can also see that if we want, for example, a weak acid to dissociate, then the presence of like a strong acid already in there will prevent its dissociation. Similarly here, we're talking about the solubility of something like calcium carbonate. So the carbonate ions are basic, so they can combine with protons. So in this instance, that will pull it to the right. So as calcium carbonate needs to dissolve, it's not very soluble. If we put acid there, then it can dissolve because the carbonate gets reacted with and taken away. This is why sometimes texts, books, or people will say that something is not soluble, but it's soluble in acid. What they're really saying is that there's another equilibrium that destroys one of the two ions and thus dissolves it. It's kind of cheap because it's like adding something else to react with it, so it's not really like a solubility anymore here. But people still kind of think about it this way, so it's important to realize, because like calcium chloride is not soluble, it will sit at the bottom. Or sorry, calcium carbonate is soluble, is insoluble, it will sit at the bottom. But if I put some acid in there, I can make it dissolve. So that's where the thought kind of comes from for that. Solubility increases in acid because the carbonate ions combine with protons, and that removes them and it drives the equilibrium to the right. Other salts that contain basic anions behave similarly, but pH has no effect on the solubility of salts that contain anions of strong acids because these anions are not protonated. So keep in mind that if you have things that are not affected by pH, then changing the pH won't affect them. I mean, it's kind of obvious there, but you know, the effect of pH on calcium carbonate has important environmental consequences. It is due to the slow dissolution of limestone under slightly acidic natural conditions. If marble, another form of calcium carbonate, also dissolves in acid, so statues or concretes or things can dissolve in the presence of acid or acid rain, and they talk about that a little bit forward, but we're not going to delve into that in great detail. It's just kind of an important thing to note at this point. So if you have complex ions, so let's talk about these. We talked a little bit before about how the addition of Lewis bases like water to a Lewis acid like the aluminum ion will create this like hexavalent shaped thing. These are called coordination complexes, or coordinate. They use coordinate covalent bonds to hold them together. Sometimes they're just called complexes. What these are is some kind of typically metal center and things attached to it, and these things are called ligands. We'll talk about this in a future lecture, but for now we're using it as an example and its formation as an example of multiple equilibria to think about Le Chatelier's principle and the common ion effect and such. So if we want to make, for example, silver chloride dissolve, silver chloride does not dissolve very well in water, but it dissolves in the presence of base, which is interesting because, you know, the chloride ion, it's not a base. The silver ion is a little bit of an acid, but not very much so. Really what it's forming is less of and you can think of the silver as acting as a Lewis acid, but it's not extremely acidic by itself. It's more that the ammonia is very basic, and it can associate with the silver ion because it's really big. So a lot of ammonias can group around it physically, and they kind of glom to it, they stick to it, and that removes the silver from the equilibrium and can drive the dissolution of the silver chloride. So as you can see here, and other bases don't necessarily work like chloride ions don't work, and you need something that's particularly the right shape and size to make this work. That's why this is more thinking of it like a complex and less like an acid-base thing, although I can see the justification for also thinking about it as an acid-base thing. There is some reasoning to that as well. So you can see the multiple equilibria that are going on, and they call this last one a KF. Now KF is the K of formation of the complex, so keep that in mind as well. And it's highly favored from the addition of these two processes. And since this is highly favored, we could couple this with the less favored dissolution and drive them all to completion. But here they just show them as the two steps forming the KF. Silver chloride is quite insoluble in water, but dissolves upon addition of excess aqueous ammonia. Okay. And talk about the formation constant, something they call the stability constant for the complex, which keeps the complex formed and not coming apart. That's like the idea. So if I combine the KSP with the KF, then I can make this much more favored. I can make this dissolving much more favored, like 7 orders of magnitude more favored. So even though it's still not, the products are still not favored, a lot more of the silver will dissolve. A lot more of the silver chloride will dissolve in this case. Because K is much larger than KSP, the solubility equilibrium for silver chloride lies much farther to the right in the presence of ammonia than it does in its absence. This addition is shown graphically. We looked a little bit at this, and it ties up the metal cation in a complex. So this idea is that if we can somehow tie up one of the components of some equilibrium, it doesn't have to be tied up in something that is permanent. It doesn't have to be removed. It just needs to be tied up in an equilibrium that is favorable to getting rid of it. That's enough to shift equilibrium, you know. And that's what they show here. The stability in this increases, the stability, increases with increasing is owing to the formation of the complex. So the solubility increases. Sorry. So also thinking about amphoterism is important, right? So water is amphoteric. It could act as both an acid and a base. We saw this before. But some other things can be amphoteric as well. In acid, aluminum hydroxide, as we show here with water, can be in equilibrium with just the aluminum ion in the water. And in base, it can add another hydroxide ion to it. So that makes it amphoteric. We can see that this aluminum hydroxide can act in either direction. It can act as an acid or a base. Many things can do that. A lot of metal hydroxides can, other than the strong bases. Other than the strong bases, many other metal hydroxides have at least some amphoticity to them. Some of them are more basic than they are acidic, but it varies. And you can see that it can dissolve completely in strongly basic or strongly acidic conditions because it can react in either direction, and it is stable between 4 and 10 on the pH scale. Calculating the solubility of a solution that contains this common ion. So we're looking a little bit back at the common ion effect problems. So if we have a common ion present here, this fluoride ion, then we add this into our existing equilibrium, and we're able to then go ahead and work out our KSP with this already present. So this is going to change our value of X. So according to Le Chatelier's principle, the calculated solubility in this is less than that in pure water, but it ends up being by a factor of what? Do they show that? Do they show what the actual number was? I'll take the book's word for it that it was 35,000, but I will, it's been many orders of magnitude here. That's what, like 5 orders of magnitude. So 4 or 5 orders of magnitude. So they check it by calculating the equilibrium concentration. They just substitute everything in. Yeah, so there you go. There's your change in your orders of magnitude. So concentrations of complex ions. So if we want to find these KFs, this can be a little more complicated. But again, we set up an ice chart so that we can develop our reasoning here. So putting down the initial concentrations of things, the change that happens, we'd have to look at this. What is the concentration in the solution? So we'll have to look up how much of it would actually be shifted if everything reacted. So they say the conversion of 0.1 moles per liter silver to consumes 0.2. Okay, right. So they'll just assume 100% conversion for this first step, which is what they had to do here. Again, some of these problems here get a little more complicated and you have to make some of these assumptions, and it's why I either wouldn't put a problem like this on the test or I would tell you to make certain assumptions, because I'm not always sure some of these assumptions are entirely obvious, right? To calculate the concentration, it's convenient to imagine that 100% of the Ag plus is converted. Well, it is, but it's not. It's a very large number, but we're going to have to make that assumption here. So we make that assumption, that subtracts this out, subtracts out the silver, and then it converts over to here as well. So we get this. We set up our equilibrium concentration expression, and then we're able to actually solve for K1 by plugging those in, coming back out and calculating a new silver concentration based on that after this equilibrium change. And of course it's a very small number because we've converted essentially all of it. We assumed that all of it was converted and then we calculated how much of it was left. I know that seems a little bit counterintuitive, but oftentimes in these equilibrium problems we do things like this as a way to greatly simplify the math, to not have to do 3 equilibrium problems when one would give us a close enough answer. Again, I would try to make this more clear when those assumptions need to be made. So we go ahead and plug this in. We see that the concentration here is essentially unchanged by the subtraction of X. The concentration of Ag NH3 plus can be calculated from either of the stepwise equilibria. So we go back to that, substitute in, and we're able to come back and get this. Nearly all of it is in this form, which is what we originally assumed to begin with. So basically we're just going back and plugging in our answers from this more significant equilibrium back into the other equilibrium that we have here. So this first K, when we have these very large Ks first, we'll tend to make assumptions that things happen and then go ahead into subsequent equilibria to make further calculations. And sometimes, as you can see, we'll have to make certain assumptions involved in that in order to make these steps work. Finally, we'll look at another example here affecting the molar solubility of silver chloride in pure water and then in the presence of the ammonia. So in pure water, we can just substitute these in. Again, we have to look up the value for the KSP because they didn't give it to us in the problem. So we go back and we get that, and then we're able to calculate the molar solubility from the balanced equation here. So then again, we'll say that with all this ammonia, it'll react completely and remove that from the system. So, but we'll need to get a new K, and we got that from the balanced equation that we were given previously. They gave us a K value looking back at earlier parts of the problem, earlier parts in the chapter when they did a problem like this. So we were able to use this value. This is, again, is the value that would have to be provided to you. You wouldn't be given a question just like this on an exam. You'd have to be given what this K value is, then work out this change and obtain the new solubility. So this is just an application of a problem type that we worked through a little bit earlier. So precipitation, right? So the question here is, if we add something or have something, a certain situation set up in a reaction, that's often a question, will one or more ions precipitate upon some addition or upon some change, or given that it's in this certain state, what direction are things going to move? Well, this is kind of a reaction quotient question. It's really similar to the reaction quotient type of situations that we looked at back in chapter 13 earlier. So we'll use the ion product, which is basically the reaction quotient for these kinds of KSP problems. We'll set that up. If the value of the ion product is greater than KSP, then the solution is saturated and it will precipitate. If it's less than the KSP, then it will not. If it's the same as the KSP, then it will not. So we're really looking for the ion product to be greater than the KSP. That's our general question here, and that's what they're looking at here. Equilibrium already exists, so it's not going to change. It's unsaturated and precipitation will not occur. Okay, so these problems are pretty straightforward compared to the other ones. Again, problems like those other ones, we'll want to make some extra adjustments to make sure that we're kind of on the ball with everything. So will it precipitate form? So what we'll have to do is look at the values of those the KSP for this. These solutions are mixed. Okay, well, these are both electrolytes, strong electrolytes, so we'd have to decide which one for a possible precipitate. We're looking here for the lead chloride that we'd be looking for a change. So we go down here, and so we go ahead and convert these into moles. That's a good first step because, again, we may have some changes in volume because of the addition of these two volumes. Then as we proceed, we're going to want to convert these to new concentrations in the new volumes. But we're really only looking at the lead and the chloride because that's the salt that will actually precipitate out. Both of these two are soluble. Nitrates are generally soluble, chlorides are generally soluble unless they're with lead 2, which is our example here. So we're really looking at, can we get the concentrations of the lead 2 and the chloride, and then take the product of those two and then compare it to the KSP. Since the KSP is 1.2 by 10 to the minus 5, again, that's something that we'd have to look up in a table because it's not given to us in the problem. I really wish the problems gave us more of these. We could then compare our ion product to that and see that it's greater, and thus we get a precipitation. Again, we talk about solubility product in acid. Again, sometimes they frame solubility as changing when you have an acid that can contribute to the equilibrium. So they give us another way to think about solubility product as one in acid. They put an A here, KSP in acid. Okay. And we can see that in acid, these values can change significantly because things can either become more soluble or less soluble in the presence of an acid based on the common ion effect and equilibrium. Will something react with that acid that'll draw it out, right? So that's the end of what we're going to present here for Chapter 15. I hope you all were able to follow along. Please do go back if there's anything confusing. Stop, look through the selections I pulled from the text. Try to work the problems out yourself in the calculator or the Google calculator. And I will see you all in the next module. Thank you.